Hey guys, let's get back to this, and now we're going to talk about specific volume. Alright, so specific volume, and we're going to talk about density as we go through this. Let's remember from our macroscopic viewpoint that's looking at the overall system. Now, typically we're going to say matter is considered to be distributed continuously throughout a region. Okay, so there's not going to be, big jump in mass somewhere in your system. Okay, now at any point the density is going to be defined as rho. Rho is going to be our symbol. So rho is going to be the mass per volume. Okay, now for symbols we're going to have m over this capital V with a bar through it. That's how I'm going to denote volume. Now you guys might want to denote it a different way, but that's how I'm going to denote it. We're going to have three different terms that have V's for symbols. We've got regular volume, we've got velocity, and we've got specific volume. So it's going to be important in your notes to make a distinction between those three V's. Okay? So this is our equation for density, and rho, or density, is an intensive property. Okay, so remember that means you can't cut it into pieces, sum up the pieces. Now this can vary with position. So just think about the atmosphere. As you go up in the atmosphere, density reduces, right? So it's changing with position. Now for our units for the SI system, notice we have mass per volume. We're going to have kilograms per cubic meter. In the English system, we're going to have pound mass over cubic feet, right? Now specific volume, we got to get to specific volume. So what this is going to be, specific volume is directly related to density, and that's because specific volume, which is little v, is just the reciprocal of density. That's all it is. Okay, so V is going to be 1 over rho. So that's your equation. So we're going to use this quite a bit. Okay. Now if density is an intensive property, that means specific volume is going to also be an intensive property. Okay, so both of those are intensive properties, which means, again, they can vary from point to point. Okay, now our units for the SI system, since we're doing 1 over density, it's basically just going to be this flipped upside down. So now we're going to have cubic meters per kilogram, and then in the English system, we're going to have cubic feet per pound mass. Okay, now you might be wondering, why do we need this? Because we already have density. Well, the problem we have with density is for a lot of the gases, the density numbers are really small. All right, and when you're doing calculations, especially if you're dividing, you don't want to divide by really small numbers. So using specific volume kind of gets rid of that issue. So let's just write specific volume is preferred for analysis because of gases with small densities. So this way we don't have such tiny numbers to deal with. All right, we'll have bigger numbers. So that's why we're going to use specific volume. And we're going to use that quite a bit. Okay. Next, let's talk about pressure. So pressure, for this one, let's look at an area. Let me draw this little area. Let's just make it look like a square. So we've got some area A, and we've got a fluid at rest, and this area A is going to pass through a point in this fluid that's at rest. Now if you think about it, this area, if it's inside this fluid, it's surrounded by fluid, right? There's fluid all around it. So that means that fluid's going to press inward on that area. All right, now if we call these forces F normal, they're all going to be the same at this point. So they'll look like that. Now remember, normal just means perpendicular, so 90 degrees. Now this normal, since it's pushing in, this F normal, that's going to be a compressive force. All right, and now the technical definition for pressure, which our symbol for this is going to be P. So pressure is going to be defined as, this is an A here, it'll be P equals the limit as A goes to A prime, I'll tell you what A prime is in just a second, of the normal force over the area. Right? So that's the technical mathematical definition for pressure. Now this A prime, this is just going to be basically the smallest area you can get that doesn't give you A divided by 0. All right. Now if you were to go through and do the limit, what you end up with is pressure equals force per area. So this is your equation for pressure that we will use. Okay. So we're not really going to use this limit equation, we're going to use this one. Now pressure can vary from point to point. So if you think about the atmosphere again, atmospheric pressure changes with elevation. So that's an example of it changing with location. Okay, so that's our equation for pressure. So it's basically how much force you have per unit area. All right. And we'll talk about the units for that in the next video. All right, so let's stop here. The next video we will talk about how to measure pressure and a few other things. I'll see y'all then.